We now demonstrate how to use Excel to run exponential smoothing and trend-adjusted exponential smoothing forecasting using the PM computer service data. In this data set, we have 12 months of data. And we are going to try the exponential smoothing approach at first. In this approach, we are going to set the first forecasting point to be the first month of actual demand. And we say, okay. For the second forecasting point, we are going to use the equation f sub t equal alpha times a sub t minus 1 plus 1 minus alpha times f sub t minus 1. That is alpha times the actual demand in the previous period plus 1 minus alpha times the previous forecasted data point. Before we say yes, I would like to remind you that we must fix the position of the alpha in this equation so that we can call this function to fill other cells. So I'm going to say yes now. That is the equation we specify for the forecasted demand function in the exponential smoothing. And I'm going to fill this function to the rest of the time period, including the next time period in the next January. So the last data point actually is our forecasting data point, okay? Now I'm going to show you how to get the error, the deviation will be equal to demand minus the forecasted data point. And we say yes. I did not calculate the deviation for the first data point because they are the same. So I just fill the rest of the data points. And then we can get the absolute value of this error. And we fill the rest of the data point. So that is our absolute error or absolute deviation for the 11 data point. The MAD will be equal to the sum of the absolute errors divided by the number of the data point, 11. So we got MAD for this exponential smoothing forecasting, given that alpha equal to 0.2. Okay, so that's our demonstration for simple exponential smoothing forecasting approach. Now, let's look at the trend-adjusted exponential smoothing. In this approach, for the first period, the trend will be assumed to be 0, okay? I'm going to demonstrate later if we change the trend value. So I'm going to set it to 0 now. The first forecasted value for January will be equal to the first month of demand. So that will be equal to 37. Now, let us follow the equation of the trend adjusted exponential smoothing, okay? So we are going to call the function of alpha times a t sub t minus 1 plus 1 minus alpha times the previous period's forecasted data point and plus the previous period's trend. Okay, so that's our equation for the forecasted demand for the next period. And we are going to fix the share of the alpha as well, so that when we use this equation to fill other cells, it will not shift the values. So we are ready to say, okay, now let's go to the trend, which is equal to beta times the current period's forecasted value minus the previous period's forecasted value. Thus, 1 minus beta times the previous period's trend. Again, we need to fix the share of the beta by adding the dollar sign. And now we are ready to say, okay, to this trend equation as well. So we have that. We have these two equations ready and put it down to fill the rest of the cells. The last point for the forecasted demand is our forecasting data point. Let's try to see the error and absolute error value. The deviation will be equal to the demand minus the forecasted data point. And we say, okay. We can come to the absolute value. And we say, okay, as well. We can select these two cells and put it down to fill the rest of the 10 cells. So we have 11 absolute error cells. Now let's go to the MAD, which is equal to sum of all absolute error divided by the number of the absolute error points, which is 11. That gives us a 3.97 MAD. Compare this MAD to the MAD in exponential smoothing. We know that this trend adjusted exponential smoothing can perform better than the simple exponential smoothing. Of course, we can change the alpha value to reflect what's happening in our analysis. And that's the beauty of adding the two value here. So we can, for example, we change it to 0.3. And we can see that the value of the MET in these two approaches change as well. Again, the trend adjusted exponential smoothing can perform better than the simple exponential smoothing. We will now show how to further improve the performance of the trend adjusted exponential smoothing by changing the initial value for the trend. In the first estimation, we assign 0 to t sub 1 in this case. But after observing the trends in the following period, it seems the value could be higher than 0. And if we take the average value of the trend following this, it seems we can take a higher value than 1, for example, 1.5, right? But before we change the value, let's look at the MET value here, which is 3.44. So if we set the trend value at 0, we get a MET value of 3.44. Now, let's change the trend from 0 to 1.5. And we'll see how will this change the value of the MAD, okay? So now, let me say yes. As we can see, the MAD value dropped from 3.44 to 2.89. This demonstrates if we can have a better trend value, the performance of the trend adjusted exponential smoothing can be better as well. So be careful when you choose the first trend value for the trend adjusted exponential smoothing. Now let's look at the graph on the right. The blue line is the actual demand data. The red line is the simple exponential smoothing without trend adjustment. And the trend adjusted exponential smoothing is in green. As we can see from the output, the trend adjusted exponential smoothing is much closer to the actual demand compared to the simple exponential smoothing. This again demonstrates that trend adjusted exponential smoothing can perform better than the simple exponential smoothing. Okay, this demonstrates how to use Excel to run exponential smoothing and trend adjusted exponential smoothing forecasting. Thank you.